Hi, in this video we will review Bayesian inference from the point of view of Chapter 9 of Pishro-Nik's probability course website, and hopefully I can give a little bit different perspective. So the chapter talks about Bayesian inference. The Bayesian viewpoint is that statistical estimation is a refinement of prior knowledge where knowledge is expressed by a probability distribution. All right, so it's mathematical representation. In certain situations, you can express your knowledge as a probability distribution. Probability distribution is a measure on a probability space. And if the probability space is a set of real numbers, then that probability distribution can be expressed typically as a density or possibly as a probability distribution if the set of numbers is discrete. Right? So here's the idea. You have your prior distribution, which we can think of as a probability density. That's a good typical example. Then you have new data, and that gives you information to construct a new distribution. Right? And presumably this new distribution is more accurate and less uncertain. It should have lower variance and have a more accurate mean. Right? So example, you have a dice that may or may not be loaded. It may or may not be fair. So you want to estimate the probability of getting a 1. Okay? Since it's a dice, six-sided dice, you initially assume the probability is 1/6. But after throwing the dice 1,000 times, you find you get 300 ones. Okay, that's highly suspicious because that's nearly 1/3 of the outcomes are 1, which seems to be too much. Okay, so this is highly unlikely, given your initial supposition. So you need to revise your estimate of P of 1. Initially, your estimate was 1 out of 6. Then, because of your new information, you can revise your estimate. The Bayesian framework gives you a systematic way of doing this. Right? You can read examples in the book. Now, here's a good example. Suppose we have yn equals xn plus wn. So these are three random variables. So let's do a specific example. Suppose that we know xn is either 1 or -1, and wn is standard normal. That is mean 0, variance 1. And one thing I didn't write down is we also suppose that xn and wn are independent. Okay, very important point. Now, the n's are not really important here. I just put them there because he had them in the book. We'll just say y equals x plus w. Right? Now, suppose we observe y, and from y we want to figure out what x was. And this is a very common case, right? When you have two options and you make a measurement, you make an observation, and the observation has some noise, and you want to figure out which of the two possibilities it was. Right? So this actually does express a common practical situation. So you make a measurement, and you try to figure out if that measurement was produced by an x that was -1 or an x that was 1. Okay? Now, in the case when x equals -1, we would have this normal distribution here. In the case where x equals 1, we would have this blue normal distribution here. Right? But that's going the other way. That's saying if I know x, this is what I expect y to be. Now, suppose y actually is here. Okay. So what was x then? Well, if x was -1, the probability density would be here. If x was 1, the probability density would be lower. So we'd expect that x is -1 and not 1. But we want to quantify that. We want a probability. We could be wrong. It is possible that x is equal to 1. All right? But here we have the conditional probability density of y, given that x equals -1, would simply be given by the standard normal density evaluated at y plus 1. The reason it's y plus 1 is because the mean is at -1. So this distance here is y plus 1. And y plus 1 is the distance from the mean, so that's the argument that you would put into the normal distribution. Okay. Similarly, if I have y here, then the probability of y given x equals 1 is the normal density, the density of W, evaluated at y minus 1, because y minus 1 is the displacement here between y and the mean of the blue distribution. All right? All right. Now that's actually the maximum likelihood choice that we saw before. This one has a higher density, conditional density, so we would choose the minus 1 over 1. But Bayesian makes things more precise. We want to recover a density for x given the observation y. And we use the Bayes formula. So you should be able to go back and always derive Bayes formula from first principles. And basically the derivation depends on expressing the probability of x and y in two different ways. Okay? You can either condition on y or you can condition on x. And then you rearrange and you get the conditional probability one way is related to the conditional probability the other way by this ratio of probabilities. Okay. All right. So it's easier to understand with probabilities than with densities, but the same principle applies. Right? So now we want to recover the probability that x equals 1 given our measurement. All right? So we know this value. We got this up before, probability of y given x equals 1. That's fine. And then the probability of x equals 1 will suppose that xn is either state 1 or 1 with equal probability. Okay, let's just say that. You all need to make that assumption. Okay. So that means we know the two terms in the numerator. Okay. And then we have this in the denominator, which just depends on y. And we can similarly find the probability that x equals minus 1, given y equals y. Now, it's important to remember that a conditional probability is a probability measure. So those two probabilities must sum up to 1. If I know y, I do know that x is either minus 1 or 1. So probability x equals 1 given y equals y, plus the probability x equals minus 1 given y equals y, must be equal to 1. All right? Okay, so we have this. So to put explicit numbers in, so if the probability of x equals 1 equals 1/2, then I can plug in what the normal density is. This is my posterior density here. Right? I have this normal form. And then same with minus 1. So I have this normal form here. Okay. And these are probabilities. They're derived based on densities, but this is probability x equals minus 1. And this is probability x equals 1. So the sum of these two probabilities, because I'm defining a conditional probability density, sum of these two probabilities must be equal to 1. Okay, and that will give me Fy of y. All right. And once I have Fy of y, then I know what these two probabilities are. And you can see the ratio here. The ratio between this probability and this probability is in fact the ratio of e to the minus y minus 1 squared over 2 to e minus y plus 1 squared over 2. In fact, it's the ratio of densities. Okay. And that comes from the fact that x was equally likely to be 1 or minus 1 at the beginning. Right? Okay, so now with these problems, you can typically just turn the crank and use the formula and find the answer. But it's good to think about what the problem is showing and get an intuitive idea of what the answer should be. For instance, we have this exercise where x is prior distribution, uniform 0, 1. And suppose we know that the distribution of y given x is geometric. Now, in practice, this could be describing the case of a component that's used repeatedly. For example, light bulbs usually blow out when you turn them on. This could be describing a light bulb whose probability of blowing out is given by x. Right? And then y would be the number of times you use the light bulb before it fails. Now we know that when x is small, the expected value of y is large, right? In fact, the expected value of y will be 1 over x. Right? If my probability of failure is 0.01, then I expect to be able to use the light bulb 100 times. Now that's an expected value. Since it's geometric, there will be some randomness. So the smaller x is, the larger y will be. In fact, if x is equal to 1, then y will be 1 with certainty. If x equals 0, y will be infinite, right? Now here we have the information that y equals 2. So what would you guess that x would be? Well, you kind of guess that x is going to be equal to 1/2, right? Because if x is 1/2, then the mean lifetime would be 2. Okay? That's not, so you kind of expect the value of x to be clustered around 2. Now, Bayesian formalism gives me a way to find a distribution of x. It doesn't say, I don't have to settle on one particular value of x, but it gives me a new distribution. But we kind of expect a distribution that's going to be sort of settled around 1/2. And to find that distribution, we turn the crank, right? Because we know the distribution of y given x. We know the prior distribution of x. Just turn the crank and you can get the distribution of x given y for the case when y equals 2. Okay, but it's good to understand what's actually going on in practical terms. Okay. Now I did point out that in this formula there's this problematic denominator. But in fact the denominator is not a problem because as I mentioned, this conditional distribution is a probability distribution. So the denominator is always determined by the condition that the sum of probabilities or the integral of probabilities is equal to 1. Okay. Now suppose I want to find the value. In this case, if I'm trying to estimate x given y, I want to find the value of x that maximizes the distribution. Now if I want to maximize the distribution, I don't care about the denominator, right? Because if I multiply or divide by a number, that's not going to change the maximum of the function. Okay. So you'll see in that maximum a priori chapter that if you want to find the maximum, sorry, this should be maximum a posteriori, not maximum a priori. Let me change that. A posteriori, okay. A posteriori means after, right? After you have received new information. All right. Now, we have in the previous chapter in classical estimation, we talked about maximum likelihood. And maximum likelihood does a similar process. It simply does not assume prior. Okay. Maximum a posteriori, I should write this, takes into account prior information. If there is prior information, it's better to use a maximum a priori. All right. Well, example 9.5 is similar to the example above, where x was binary. In this case, the signal x is normally distributed. Now, when you do send information over the air, say in wireless communication, you don't have information quantized with -1 to 1. Typically, you have information that's quantized at several levels. So this is one possible model for information that's sent over a wireless communications channel. And then you have W, which is the noise. You have other signals passing through the air that corrupt the signal that you have. And typically, these corrupting signals are modeled as Gaussian. And that's because they're sum of a lot of random effects. And typically when you have the sum of a lot of small random effects, you get a random variable that is Gaussian. Right. Now, we have these two problems here. You can find the maximum likelihood estimate of x given that y equals y, and find the maximum a posteriori estimate of x given y equals y. And let's just intuitively see what we would expect the difference between these two to be. All right. So let's specialize to the case where the variance of the signal and the variance of the noise are the same. They're both 1. And we can intuitively understand this situation a little bit better. Okay, so here's my distribution, or my density rather, for x. And of course, x is not what I observe y. So suppose I do observe the value of y here. All right. And I want to recover the value of x. All right, so suppose I observe this value, then what's the maximum likelihood value of x? Now, what does maximum likelihood value mean? Well, what it means is that I fix a hypothetical value for capital X, and then I figure out what the probability density of W would be to produce the value of Y that I see. All right, so I fix the value of X, and then I say, okay, if this value of X were true, then what would be the probability density of W to make Y happen? Right now, so in this case, suppose I observe y, and I choose that value x, that hypothetical value x, to be equal to y. Right? In that case, what's the value of w? Well, that means that w is 0. Now, w equals 0 is a very unlikely outcome. However, the density at w equals 0 is maximized. Okay? So we say that's a relatively likely value. In fact, that's the most likely. Again, I want to emphasize that likelihood is not a probability. It's just kind of a plausibility. Okay. So x equals y is a plausible value because that produces w that is relatively likely compared to other possible values of w. So that's the reasoning that goes with maximum likelihood. Now, maximum a posteriori is much more systematic and uses the information that I know that x has a normal distribution. Right. Now, we know how to compute this. We turn the crank and get this result. But let's consider what would we expect to be different for maximum a posteriori from the maximum likelihood estimate. Will we expect the x to be bigger or smaller? Now, when we did maximum likelihood, we only considered the probability density of W. We didn't consider the probability density of X. So we supposed this value of X, X equals Y, and then inferred a density for W. However, this value of X is rather unlikely because it's large. It's far from the mean. Okay. So if we consider the probability density of X also, we kind of expect a priori that x, the value of x will be smaller. What we suppose happened here, if I get this value of y, is that we expect that x would be positive and w would be positive, and the deviation of both x and y would contribute to the deviation of y from the mean. So I expect the a posteriori estimate of x to be smaller than y. In fact, since in this case, if x has the same standard deviation as W, symmetry would tell me that the maximum a posteriori value of x would be y over 2. Because then half the deviation from the mean would be due to x, half would be due to w. In fact, as a general rule, before you do a mathematical problem, it's good to try to anticipate what the answer might be. And then when you get the answer, you can see, well, does this make sense with what I expect the answer to be? Right? Now, to find the answer, we just turn the crank. Because we know the density of x, we know the density of w, we know that x and w are independent. We can find the density of y given the value of x, which is just going to be the distribution of w. If we do work through the details, you see this the conditional distribution of y given x is the distribution of w plus x, given x equals the observed value of x. So that's simply the density of w evaluated at y minus x. Similar to the example I did above in the binary case, that the difference between y and x must be due to w. Okay, then to find the value of x that maximizes the a posteriori density, you want to consider this numerator as a function of x and find the maximum value. Find the x that gives the maximum value. So this here is normal. As a function of x, this is normal with mean y. As a function of x, this is normal with mean 0. Now, if the two normal random variables have the same have the same standard deviation, and we want to maximize the product, symmetry would tell us that the maximum must be halfway between the two means. Because as you move farther away from 0, this one becomes smaller. As you move farther away from y, this one becomes smaller. So the happy medium is when the x is halfway between the 0 and the y. And that turns out you can actually do the derivative and find that. And one of the techniques that is introduced in the chapter is, instead of minimizing the product of distributions, minimize the log of the product. Since log is monotonic, the maximum of the log will be equal to the maximum of the product. And if you just take the log of this product, you take off the exponential, you can see it's a very simple quadratic function. And the coefficients of this quadratic are all negative. So maximizing this quadratic with negative coefficients is the same thing as minimizing. I should put a positive coefficient here, and that should be a plus and not a minus. And just put a plus there. Okay. So I minimize the, oops, why is it not working for me? There we go. Minimize this expression. Oh, that's terrible. All right. Well, should be a plus. Let's just get it in there. Okay. Does it go down here? Okay. Should be a plus. Right. Okay. That's a plus. Okay. And then this is minimized when x equals y over 2. Okay. Now, the maximum a posteriori estimate for a parameter is not the only way to estimate an unknown parameter. There's also minimum mean squared error. And I think probably minimum mean squared error is more common than maximum a priori. The idea of minimum mean squared error is very simple. What you're trying to do is find the value for your unknown parameter that minimizes the expected mean squared error. Okay. That's, and that you know, mean squared error is kind of related to variance. Okay, so it's in fact it's sort of a conditional variance conditioned on you choose that value as your estimate of the unknown parameter. So in terms of properties of the distribution, maximum a posteriori estimate is the mode of the posterior. The minimum mean squared estimate is the mean of the posterior distribution. And he proves that, and I want to give a different perspective on that fact and use linear algebra to show the same thing that he shows in section 9.15. Okay. Now, the mean squared error corresponding to the mean of a distribution is the variance. Okay. Because it's the expected value of the difference between the value and the mean squared, which is the definition of variance. And any other value gives a larger mean squared error, and we'll show that below. Okay. All right. By mean squared error, I mean the expectation of the random variable minus a given value squared. Okay, so it's the mean squared error, mean squared residual. Okay. Now he gives a proof of this in the chapter. I want to give an alternative proof that compares random variables with vectors. And this is a very important comparison. And this adds richness to your understanding, both of linear algebra and of probability, if you understand this relationship. That, in fact, random variables can be considered as vectors. they satisfy all the vector space axioms. And in fact, this is because random variables are functions. Real valued functions on a set can be considered as vectors. Now, that was also mentioned in the linear algebra course. Right? So in particular, we have mean zero random variables, and they form a subspace. You can verify that any linear combination of mean zero random variables is still a mean zero random variable. So that's a perspective on mean zero random variables. You're just taking a subspace of the entire set of random variables. Now, if you have two random variables and take the expectation of the product, it turns out that's an inner product, just like the dot product, and has the same properties as the inner product. And a lot of the inequalities, like the Cauchy-Schwarz inequality, that hold for vectors also hold for random variables. And you see this kind of thing all the time. All right? Now, the relationship between probability spaces and random variables can be seen most clearly when you have a uniform, discrete probability space. For instance, suppose you have n points, and each point has the same probability. Right? Typically, we label points in a probability space as omega. And omega don't have to be numbers, they could just be outcomes. One uniform probability space would be the rolls of a dice, right? In that case, you have 6 outcomes, and the probability of each outcome is 1 over 6. Right? Then any random variable can be identified with a vector of values of that function on the points in the probability space. Right? So it's a vector. In fact, it's explicitly a vector. Okay? And you can see that if I have two random variables, the expected value of the product of those two random variables is just the dot product, ordinary scalar product, of these two random variable vectors divided by n. And 1 over n does not change the properties of the inner product. Right? So in fact, when you have the expected value of x and x times y equals 0, that can be interpreted as orthogonality. So in particular, if you have mean zero random variables that are uncorrelated, we can think of those as orthogonal. Now we know a lot about orthogonal vectors. We know the Pythagorean theorem. Okay? The Pythagorean theorem doesn't just hold in 2 dimensions, it holds in any number of dimensions. Pythagorean theorem tells us that the length of the sum of vectors is the squared length of a sum of vectors is the sum of the length squared of the first plus the length squared of the second, when and only when x and y are orthogonal. Right? That's an important condition. Right? Pythagorean theorem only holds for right triangles. If it's not a right triangle, it doesn't hold. So how does Pythagorean theorem give us insight into random variables? Well, so we have seen that the expected value of x minus minus expectation of x is 0. Right? If you remember how to show that, expectation is linear, so I can take the expected value of x minus the expected value of the expected value of x. But the expected value of a constant is always just the constant. So that's where this equation comes from. I can interpret this equation as saying that the random variable x minus expectation of x is orthogonal to the constant random variable. Right? Constant random variable is just the random variable that takes the value 1 on every point in the sample space. Now, since this random variable is orthogonal to 1, it's also orthogonal to any multiple of 1. Okay? So x minus expectation of x is also orthogonal to this random variable. Right? Then the minimum mean squared error condition pops out immediately. Because if I take this is basically the length squared of this vector here. If I take x minus expectation of x plus a squared, right? This here's a constant, and this here is my random variable. Right? And now here I just distribute the minus, And then I can write this as a sum of two vectors, x minus expected of x, and then minus a, right? So this expectation, which is the mean squared error, which is the squared error from this value, expectation of x plus a, okay, the squared error based on this value is equal to the squared error based on the mean plus a non-zero term. Right? So that tells us that the expectation value of x is the best choice if I want to minimize the expectation of the squared deviation. Okay, so that's enough for one video, and hope that gives you a little bit different perspective and a way of thinking about these problems without just using the equations. All right, thanks for watching.